8.5 is not difficult, but there are some moving parts, and you, I guess, try to listen so that you can, it would be difficult to figure out 8.5 by yourself, is what I'm trying to say. So we're talking about rational functions. The very first thing in 8.5 says that it defines a rational function, but basically this is just a fraction. So we've got one function on top of another function is basically what it is, but we've got a function as a fraction. So we're going to kind of go slow with the first, but this says consider f of x is equal to 1 over x minus 3. Find the domain of the graph f, which is one of the reasons why we went back and covered 5.1, because we talked about the fact that you can't have the denominator equal to 0. That's when it's a problem in the domain. So you would solve that and you would say, well, x cannot be equal to 3. So when we talk about our domain here, we would say all x's such that x is real and x is not 3. In interval notation, we would say we're good from negative infinity to 3, and then we're good from 3 to infinity. So something happens there at 3 that causes us a problem. In this graph, you can see that the thing that happens is there's a kind of like at x equals 3, there's kind of a break in the graph right here. And that little break in the graph is called a vertical asymptote. That's a weird name. But vertical asymptote is kind of something that splits the graph right in half. Right? We're going to go over that a little bit more as we go through this. Example 2, determine the domain of each of the functions. So I'm looking at the denominator. The denominator cannot be equal to 0. So there's nothing to solve on this one. We would just say it's all x's such that x is real, but x is not 0. We could say in interval notation, we're good from negative infinity to 0, and then we're good again from 0 to positive infinity. Because on our graph, you can see that we've got right here where x is equal to 0, we've kind of got a break in the graph, a vertical asymptote, kind of splits that graph right into two parts. So on this one, we're still worried about that denominator, and 2x minus 6 cannot be equal to 0. So we would add 6 to both sides and we would get, okay, 2x cannot be equal to 6. And we would say, okay, we must have a problem at 3. And so at 3, if you look at this graph at x equals 3, that's where it's split right in two. That's a vertical asymptote. We would say on our domain, all x's such that x is real and x is not 3. So we're good from negative infinity to 3, and then we're good again from 3 to infinity. Okay, so that's really all we've talked about so far. And in 5.1, we really talked about what the domain could be and what it couldn't be. And this kind of goes into why is that? Well, we're going to have a split in the graph right there. There's going to be a vertical asymptote. So it says if A is a 0 of the denominator, both of these say the same thing. So it's a little bit clearer here. If A is a 0 of the denominator, but not the numerator, then the line x equals A is a vertical asymptote for the graph of the function. Okay, so if I have, this is what this is saying. If I have x minus 2 times x over x plus 3 times x minus 2, do you see how these x minus 2 and x minus 2 is the same? Okay, If that happens, this is an example of when you don't have a vertical asymptote. This is a no vertical asymptote. I'm not going to spell all that word out. It's right here. If they're the same on the top and the bottom. So what this is saying is the opposite. It's saying if you don't have the same thing on the top and the bottom, then you do have a vertical asymptote. So at x plus 3, there's a 0 there. That would be a vertical asymptote. If you can get something to cancel out, so at 2, those would cancel out. Not a vertical asymptote, but there would still be one here at x plus 3 on this one. Okay, and we're going to work a lot of examples where this happens, but I'm just trying to explain what this wording means. So on this example 1 here, I don't have the same thing on the top and the bottom. So I would have a vertical asymptote at whatever the 0 is on the bottom. So the first thing it says is to factor and reduce if possible. Well, x minus 2 over x plus 3 does not factor or reduce. I'm done. There's nothing I can do to that. There's going to be sometimes when you can. So if I want to look at the domain here, I'm going to have to say, when is x plus 3 not equal to 0? So we would solve that and we would say, well, if we subtract negative 3 from both sides, that happens when, so x cannot be equal to negative 3. So when we're actually stating our domain, we could say it 2 ways. We could say all x's such that x is real and x is not negative 3. Or we could say we're good from negative infinity to negative 3, and then we're good again from negative 3 to infinity, because at that place, there's supposed to be a vertical asymptote. Usually at this point, I like to go to my graphing calculator and I like to look at what the graph looks like. So I go to y equals and alpha y equals, because I'm typing in a fraction. This one was, sorry, x minus 2. Yes, sir, over x plus 3. And I like to kind of look at the graph to see if I'm on the right track. And if you look at this graph, you do see that there is something going on right here at negative 3. Right, you could draw a vertical line. There's a vertical asymptote there. There's a problem on the graph there. So when we go here, we can kind of verify, yeah, we do have our vertical asymptotes or whatever our zeros are. And we've said that that's where your problem is in the domain. So we do have a vertical asymptote at x equals negative 3. It's that easy. All right, let's talk about this. To find x-intercepts and y-intercepts. You guys should already know something a little bit about x-intercepts and y-intercepts. You should know that if you want an x-intercept, that y is equal to 0. And if you want the y-intercept, that x is equal to 0. And the goal is to find the other part. So there's several ways we could do this. We could go to our table and hope that the answers are there. Like look at the table and find where y is equal to 0 and look across and see what x value is, and vice versa. Or we could just solve it. So if y is equal to 0, we're talking about this function right here. F of x is the same thing as y. So if I'm just going to solve it, I would say, well, here's what I know about this. Y is equal to 0. I need to figure out what x is. So I could, to get rid of this on the bottom, I could multiply. Let me just write this down so it's easier for you to see. If I multiply both sides by x plus 3, whatever, if I multiply by the denominator, that's going to make that denominator cancel out. Well, x plus 3 times 0 is just 0 equals x minus 2. These two canceled out, so I multiply by the denominator to get that to cancel. And then I would just add 2. So x is equal to 2. That would be my x-intercept. There's a trick to that, okay? And I'm gonna keep working these a long way until you guys can tell me what the trick is, but when we actually got it down to the part we were solving, it looked like this part right here, 0 is equal to x minus 2, because we multiply by the denominator and it canceled out. So really, we're only, if you can find the zeros of the numerator, that's your x-intercept. You can just go straight to your numerator and write x minus 2 equals 0, because that bottom part's gonna cancel out because you're multiplying it by 0. Okay, so the trick is that you can just do the numerator is equal to 0 and solve it to find your x-intercept. To find your y-intercept, well, this is kind of easy because you're going to take whatever x is and make it 0. So I'm just plugging in zeros for x's. That's your zeros are going to go away. So you're just left with negative 2/3. Everything else kind of collapses out of that. That's not a 0. That's not an x. Okay. Everybody okay with that? Okay. So here we go. The first step of this is asking us to factor this. So they're wanting us to factor x squared minus 4x over x to the third minus x. I'm looking at the top of this and I'm seeing that both x squared and negative 4x have at least one x in them. So I can pull an x out of that, which is one of the reasons why in the support you've been working on doing this so much, like multiplying these out, factoring these. So I can pull an x out of both of those. That's going to be x minus 4 would be left. If you take an x out of x squared, you're left with x. If you take an x out of negative 4x, you're left with negative 4. On the bottom, I can take an x out of that as well. So if I take an x out of x to the third, I have x squared. If I take an x out of negative x, I have just negative 1. And actually, I can keep going on the bottom with factoring because x squared minus 1 is the difference of squares. We've talked about this a bunch. X minus 1 times x plus 1. If you don't know how to go from x squared minus 1 to see if it's going to factor anymore like this, what could you do? You could go to the quad function, right, and type in a is 1, b is 0, c is negative 1, and it would tell you it's negative 1 and positive 1, and you would know those would be your zeros, and so you could make the factors out of that. So if you're really stuck on the factoring, you always can go backwards. So the domain potentially has some problems. The problems in the domain could occur when we are looking at our denominator. So we could have a problem. X is not supposed to be equal to 0. X minus 1 is not supposed to be equal to 0. And x plus 1 is not supposed to be equal to 0. Those three things. This one's done for me. I can't solve that one. X is not supposed to be equal to 0. I can add 1 and get x is not 1. Subtract 1 and get x is not supposed to be negative 1. Everybody okay with that? So we're just focusing on what's in the denominator. So we would say our domain is all x's such that x is real and x is not 0, negative 1 and 1. You could also write that as we're good from negative infinity to whichever one of these comes first. So you would say negative 1. We're good again from negative 1 to 0. We're good again from 0 to 1. And then we're good again from 1 to infinity. That one's kind of crazy. Any questions about that? So we're factoring it. We're looking at what the zeros are in the denominator. Okay. Going back to the very first thing that we just talked about in the beginning was we had this statement that said, if you have any factors that are the same in the numerator and the denominator, those are not vertical asymptotes, right? And we've already got the graph, so I don't need to go to the graphing calculator here, but it's easy to see that at x is equal to 1 and x is equal to -1, there are vertical asymptotes. Because right through -1, there's a dotted line or dashed line drawn, and right through 1, there's a dashed line drawn. It's easy to see that. But there was another problem, right? This one right here, x is equal to 0. That would mean there would be a line drawn right through x equals 0, and there's not. You can see part of the graph that goes right through it. So that is not a vertical asymptote. Why is that the case? Because when you look at your original factored problem, we had something that was exactly the same on the top and the bottom. And that one was the one where x is not equal to 0. Those canceled out. If it cancels out, it's not going to turn into a vertical asymptote. Instead, it is a hole. We have in our graph, we have a hole at x equals 0. So if we were to zoom in really, 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 really close on our graph, there would be a little hole right here. It wouldn't be filled in. Why does it look filled in on the graph? It's easier than you would think. The reason that it's filled in on this graph is because we are not zoomed in really close. And if we could zoom in really, really close, we'd be able to see the hole. But the hole is exactly at x equals 0. So at x equals 0.00 something even the tiniest bit bigger than 0, 0.00000001, there is a value. So it gets really, really close to 0 from both sides, but it just never touches x equals 0. At x equals -0.00001, there's a value. So it's really hard to show that hole. If I'm drawing a hole there but in reality, I can't even really draw it because I'm just representing it there. But even at a place that's very, very close to 0 would have a value. I don't know if I explained that good enough. Are y'all good with that? Yeah. Okay. So what do you know about x-intercepts? One thing you know about x-intercepts is that y is equal to 0. One thing you know about a y-intercept is that x is equal to 0. When you're looking for the x-intercept, the trick is that you find the zeros of the numerator, because the denominator is going to divide out. So we're just looking at our numerator here. In our numerator, the easiest way to find the zeros is to go, when we factored, it was x over x minus 4. We want to know, when is that equal to 0? Well, it's either equal to 0 when x is 0, and it could possibly be equal to 0 when x minus 4 is equal to 0. Those are the two times it can be equal to 0. So we would have to solve this part and get x equals 4. So we have two answers. One of the answers is 0 and the other answer is 4. You need to go back and think about what you know about this. Do we have a 0 at 0? We just figured out x equals 0 is what? A hole. So you need to mark that one out. We don't have a 0 at x equals 0. And you can see it on the graph. There's that's not an x-intercept up here. Okay, but we do have one at x equals 4, y equals 0. That is an x-intercept. So you need to go, yeah, always go back and look and make sure you don't have a hole at that point that they're saying is an intercept, or that we're figuring out as an intercept. Everybody okay with that part? It's kind of to me, this is one of those where it gets a little bit confusing because we've got so many moving parts. So just stop me if you get confused. If x is equal to 0, all we have to do is go back to our original equation that said x squared minus 4x over x to the third minus x. And instead of all the x's, we know x is equal to 0. We're going to plug in 0 every time we see an x. Okay, so this whole thing would be 0. Do we have a y-intercept at x equals 0, y equals 0? You want to go back and say, is that a hole? There's a hole at x equals 0. So we don't, look at your graph. Does this thing ever cross the y-axis? No, because at the place it's supposed to is a hole. So we don't have one. Okay, so you've got to go back and make sure. That's why they ask you, do you have any holes in the graph? You want to check that first. Where does a hole happen? So far, what we've done is we have said, just because we're fixing to add on a little bit. What we have said is, if you have something on the bottom that is not okay in the domain, in other words, it's equal to 0, that's a vertical asymptote. Okay, if you have something on the bottom that makes it equal to 0, that is a vertical asymptote, unless one case, right? And that one case is if the thing is that's on the bottom is also on the top. And in that one case, that point is a hole and not a vertical asymptote. So we went down here on this one and we factored this out and we said x minus 1 and x plus 1, those two produced vertical asymptotes because they didn't have, there's not an x minus 1 and an x plus 1 on the top. So those two were vertical asymptotes. The x is equal to 0, we did have the same thing on the top and the bottom, so that was a hole. That's all we've done so far. You look at your zeros on the bottom, those are vertical asymptotes, unless something cancels out with the thing on the top, and then it's a hole. Does that make sense? Those are the two things we've done. And if it's a hole, it's not an intercept, it's a hole. You're done with that part. And we're going to keep talking about this a little bit more, but okay. So this kind of gives you an example. So this is talking about the horizontal asymptotes. So when the numerator and the denominator of a rational function have the same degree, then the line y equals a over b is a horizontal asymptote. Here is a visual example of that. If I wrote down my equation was y equals 3x squared over 2x squared. The leading coefficient, both of these are raised to an x squared. That's the highest power of x. So they are, the numerator and the denominator have the same degree. So they're both x squareds. Then my horizontal asymptote is going to be whatever the coefficients are, 3 over 2. Now horizontal is going to lie flat. We really haven't talked about, we're adding this on. So if they're exactly the same, it's going to be whatever numbers are in the front. If the degree of the numerator is smaller than the degree of the denominator, I call this bottom heavy. Then you do have a horizontal asymptote. It is the line y equals 0, and the line y equals 0 is just the x-axis. So if it is bottom heavy, you're going to have a horizontal asymptote at y equals 0. We're going to go over this stuff, but this would be an example of that. If I wrote down 3x squared over 3x to the third, that one is bottom heavy because x to the third would be bigger than x squared. This would have a horizontal asymptote at the x-axis. If the degree of the numerator is larger than the degree of the denominator, which is going to be top heavy, then we don't have a horizontal asymptote at all. We don't have one. So if it was 3x to the third over 3x squared, we don't have a horizontal asymptote because it's top heavy. So those are the examples you kind of need to remember. We're going to go slow on trying to remember this, but this is a good place to go back and look to help you. The graph of a rational function never crosses a vertical asymptote, but sometimes it does cross a horizontal asymptote, is what this is saying. So here we go. You're going to need to go and circle the highest power of exponents you have on an x. It's not always going to be the first term. It is here, but sometimes they might try to trick you and put it in the middle. But 6x to the fourth would be my high, four is the highest power on any x I have on the top row. On the bottom row, 4 is the highest power on any x I have on the bottom row. So I'm going to circle that. So is this degree the same, top heavy or bottom heavy? It's the same. And if it's the same, then it does have a horizontal asymptote. And it is going to be whatever your leading coefficients are. So it would be 6 over 9. You're not worried about the rest of the stuff. And we could reduce that to 2/3 if we divide both of those by 3. So this would be our final answer. Y equals 2/3 would be a horizontal asymptote there. And we'll talk about what a horizontal asymptote looks like in a minute, but we need to be able to pick them out first. You're going to do the same step here. The highest power exponent I see on an x here is 2x to the first power. The highest power I see on this one is going to be this x to the third. Are those the same powers? Is this top heavy or bottom heavy? Okay, if it is bottom heavy, then we want to go back and make sure that we're using the right rule, because it tells you right here, if it's bottom heavy, oh, you have a horizontal asymptote at y equals 0 or the x-axis. So y equals 0, which is the same thing as the x-axis. You have a horizontal asymptote there because this is bottom heavy. Same thing here. The highest power exponent I have on the x is an x to the third. The highest I have on this one is an x squared. So this is top heavy, right? So this does not have any. It does not have a horizontal asymptote. Top heavy does not. Bottom heavy is the x-axis. Okay. So there's an example of each of those. It's not terrible. It's just trying to remember all the parts, which can be a little bit difficult. Okay, so let's look at these graphs. They want us to graph 2x minus 4 over x minus 1. First thing you want to do is look at the factors if you can. So I'm looking at 2x minus 4, and I think I can take a 2 out of 2x, and I can take a 2 out of negative 4. So that would leave me with x minus 2 if I did that. If I take a 2 out of 2x, I've just got x. And if I take a 2 out of negative 4, I've got negative 2. And on the bottom, I've got x minus 1. So this situation with the domain does not change. You always look at your denominator and say, well, that can't be equal to 0. X minus 1 can't be equal to 0. So that only happens in this case where at 1. So my domain would be all x's such that x is real and x is not 1. In interval notation, negative infinity to 1 is okay, and then we're good again from 1 to infinity. At this point, because I always second guess myself, I would go to my graphing calculator and I would type in my function. I would just make sure that it looks like there's a problem at 1, you know? So I would go graphing calculator, I go to y equals, I can type in my function of, sorry, I wasn't keeping up. I can type 2x minus 4 over x minus 1. okay? And I like to look at the graph and see, it does look like there's something going on right there, right? There's a problem at 1. It looks like we're being split right there. Also looks like, just to note what we're fixing to do in the middle, it looks like there's a problem up here. That would be a horizontal asymptote that we haven't really talked about yet, but it looks like it's being split that way too. So I'm going back to my graph, or back to our problem, because it's saying that, what are my vertical asymptotes? You have these, whatever your answer is for your domain is your vertical asymptote, unless something cancels out on the top and the bottom. And it doesn't. I don't have x minus 1 on the top. If I did, it would be a hole, right? So it's a vertical asymptote. We already know that. So I go to my graph at x equals 1, and I just draw like a dashed line through there, because I know I'm not going to touch that. That's my vertical asymptote. When you get to the part with the horizontal asymptotes, the questions you're asking yourself is this top heavy, bottom heavy, or are the same, right? So you would go to your problem and you would look at your leading coefficient. So the highest power exponent on the top would be the x to the first, and on the bottom, it would also be the x to the first. So this one is the same, right? So that means you look at your leading coefficient. So I would have a 2. And then on the bottom, it would be a 1x. So it would be over 1, which we know that that is just y equals 2. That's going to be a horizontal asymptote at y equals 2, which that's why I said, look, it's splitting up there a little bit. Well, that's my horizontal asymptote. If I want to find x equals 0, then that means that, I mean, the x-intercepts, I'm sorry, x-intercepts happen when y is equal to 0. I'll worry about what's x. And remember that you just have to do the zeros of the numerator. So we just have to look at, when is 2x minus 4 equal to 0? So we would add 4, 2x is equal to 4, divide by 2. Exactly. So x is equal to 2. So that point, well, first off, I would say, is that a hole? No, it's not, because this one didn't have any holes. We didn't have any of the same things cancel out on the top to the bottom, right? So we don't have to worry about holes on this one. So the point x equals 2, y equals 0 is one of the points on the graph. And I'm going to go ahead and fill that part in. And then my y-intercept is when x equals 0. What is y? And if we go to our regular function, instead of x's in there, we would plug in zeros there. So you should be just left with your whatever terms don't have x's. So -4 over -1, which is just 4. So the 0.04 would be my y-intercept on this one. We didn't have any holes in this graph. Nothing canceled out. Okay. Well, let's do at least, I think there's 2 more graphs that we can kind of go through this process on. That should help. An oblique asymptote is a slant asymptote, and it happens whenever the degree of the numerator is 1 greater than the denominator. We're not going to that level, but an example of that would be like if you had an x to the 3rd over an x squared, 1 degree higher, that has an oblique asymptote, which means that it would have an asymptote that kind of was slanted like this. So at least you've heard of that. It only happens when it's 1 degree higher. Okay. First step, factor. So if you don't have any clue how to factor this x squared minus 1, so what we're trying to do is factor x squared minus 1. What are you going to do? Trying to divide it up into those 2 factors. I know it's the difference of squares, so I can recognize that real quick. That's exactly what it is. But if you don't know that, what could you do? So go to your quad program, right, and find the zeros. And if you typed in A is 1, B is 0, C is -1, it would tell you that your zeros are -1 and +1. And from that, you should be able to go, oh, it's the opposite of those. So X -1, X +1. You should be able to get that if you can find your zeros. On the bottom, same thing, X squared plus X minus 6. If it says to factor it, you should be able to come up with your zeros. So if you type this in the quad program, it would tell you your zeros are -3 and +2. And then you would need to do the opposite of those. Okay, but that'll work. When we're looking at the domain, so that if you're following along on Zoom, if we're looking at the domain, then where are we going to have problems? This is our question for Zoom people to fill in chat. Where are we going to have problems in our domain? At what places? Always worried about your denominator when X plus 3 cannot be equal to 0 and X minus 2 cannot be equal to 0. So we would solve these. So X cannot be -3 and X cannot be 2. And remember the way that we write this, I'm going to have to kind of carry this over, sorry. So the way that we would write this is that we're good for all X's such that X is real and X is not 2 or -3. We wrote it in the interval notation. We're good from -infinity to -3. We're good again from -3 to 2. And then we're good from 2 to infinity. You always go from the smallest to the largest. Is there anything that cancels out here? No, nothing the same on the top and the bottom. So I don't have any holes to worry about. So that means that X is equal to -3, whatever my domain problems were, should be asymptotes. And X is equal to 2 should be asymptotes. At this place, I like to go to my graphing calculator just to make sure that I have factored, first off, that I've factored correctly. So I go ahead and plug in the original equation, the X squared minus 1 over X squared plus X. Yeah. Sorry, I type slow, but if I get in a hurry, I start making mistakes. So X squared plus X minus 6. And I go ahead and look at the graph. Okay, so that's giving me the idea that, hey, look over here at -3. There does look like a problem at X equals -3, and at +2, there does look like a problem. Vertical asymptote. There looks like there might be a horizontal asymptote too. Something cutting it this way. So I go back and I say, yep, X equals -3 and X equals 2. Those are asymptotes. We got that right. So we would come here and draw them. -3. Okay. Horizontal asymptotes, that's the thing that you look at whenever you're saying the same top heavy or bottom heavy. So we're comparing this and we've got the highest power of exponent I have on the top is the squared, and on the bottom it's also the squared. So I have an X squared over X squared. Those are the same. So that means Y equals, my coefficients are 1s in front of these. So it would be 1 over 1. So I do have a horizontal asymptote at 1. And we already kind of looked at the graph and said, yeah, there is something that's kind of making that have a division there. So oblique asymptotes only happen whenever the degree on the top is one higher than the bottom. We're not doing those in here, so you should write none. The x-intercepts are the zeros of the numerator. So x squared minus 1. When does that equal to 0? You could use the quad program, or you could just solve this. It doesn't matter, but that will tell you what the zeros are. So x is equal to plus or minus 1. So when y is equal to 0, x is equal to 1 and negative 1. I don't have any holes in this graph because nothing canceled out in that first step. So those both should be there. Negative 1 and positive 1. My y-intercepts happen whenever x is equal to 0. So you could go to your original equation. So instead of x's, you would plug in zeros for your x's. But everything else should go away. So if I plug in 0, that would be 0 squared minus 1 on the top. And on the bottom, I'd have 0 squared plus 0 minus 6. So I would be left with negative 1 over negative 6, because these zeros are going to go away. So I've got y is equal to 1/6. And the 0.016 is just going to be just a tiny bit. We don't have any holes, so we don't have to worry about that point not being there, but it's just a little bit above 0. And if y'all remember from the graph, it kind of looked like this. So we can kind of draw that, go ahead and draw that part. But those are not enough this time to fill this up. Let me show you what, let me remind you of what it looked like. So this is what it looked like. So on the top part, it kind of went out like this. So we do need to find some x values on both sides. What can we do to get those x values? Second graph, go to your table. And I'm not going to do that, but I went ahead and wrote down some values. So we need to look at, like you want some over here, like at -4 and -5. We need to know what those values are. And we need some over here. So I picked 3 and 4. Doesn't really matter what you pick as long as you can fill in your graph. So 3 was 1 1/3. 4 was 1 1/14. -4 was 2.5. And -5 was 1 5/7. So -4, 2.5. -5 was 1 5/7. So about right here. And remember that the graph kind of did something like this. You're going to have to kind of make it look like the graph because these are a little bit weird. 3 is 1 1/3. And 4 was 1 1/14. So like barely above that little line. I'm probably not even making it close enough, but it's really, really close to that, but it doesn't touch it. So that's kind of what that graph looked like. Are y'all okay with that? Okay, one more. Because we could do these all day long, and it's like you got to start practicing some yourself and following these steps. But here we go. So first step is we want to factor this. So x minus 2, there's not going to be anything on the top that's going to be able to go into x minus 2. So that's part's done. So on the bottom, you could use the quad program and find your zeros and do the opposite of those. Or you could factor it by saying what multiplies to -2 and adds to -1. That's going to be x minus 2 times x plus 1. So if you did the quad program on the zeros would come up as +2 and -1, and you would do the opposites of those, right? Okay, anybody have problems with that? Because if you get stuck there, you're going to be in trouble. You do the opposite of whatever your zeros were. Okay. So our domain is always a problem in the denominator if either of those things are equal to 0. So x minus 2 cannot be equal to 0, and x plus 1 cannot be equal to 0. So we would solve those and say we got a problem at 2, and we have a problem at -1. So when we're actually writing the domain, we would say all x's such that x is real and x is not 2 or -1. We're good from negative infinity to -1. We're good from -1 to 2. We're good from 2 to infinity. Those places are supposed to be my vertical asymptotes. Unless, what? Something cancels out because they're the same on the top and the bottom. And this time there is something that's the same on the top and the bottom. So it looks like x minus 2 over x minus 2, those would cancel out because they're the same on the top and the bottom. Even though one's not in parentheses, I can stick a parentheses around that. But x minus 2 is the same on the top and the bottom. That, and it's not written on this paper, but we would have a hole at that place where x is equal to 2. I'm going to make a note of that. I'm going to have a hole at x equals 2 because they're the same. I should have a vertical asymptote at the other point, which is -1, because it did not cancel out. Okay. So I like to make sure of that at this point. So I go to my graphing calculator and I type in alpha y equals for my fraction. And we want to do x minus 2. And I always plug in before I factor it, because what if I make a, or what if I factor it wrong, I guess. This helps me to kind of figure out, did I mess up something? Because this is not panning out right. So minus x minus 2. Right, and then I would hit graph to kind of look at it. It does look like I've got some kind of split in my graph right here at -1. And it might also have a horizontal asymptote going this way. So kind of keeping that in mind. So I thought I had a vertical asymptote at x equals -1. I have verified that on my graph, so I'm going to go ahead and draw that. Okay. Horizontal, so if you're following online, tell me what the answer to this is in your chat. Horizontal asymptotes occur when you're looking at the things like, is it top heavy or bottom heavy or the same, right? So you want to go to your original function. And what I want you to tell me is, if you're following on Zoom, if it's top heavy or bottom heavy or the same. But you want to circle your x's to the highest power. I have an x to the first on the top and an x squared on the bottom. So it's bottom heavy, right? That's what you should be typing in. What does bottom heavy mean? So y equals 0, which is your x-axis, is a horizontal asymptote, which we suspected when we went to our graph a while ago. We saw that it kind of had a break right there. So we're coloring that part in. Slant asymptotes only happen if the numerator is 1 higher than the denominator, like an x to the third or an x squared. We're not doing those in this class. X-intercepts, you find the zeros of the numerator. So we really are only worried about when x minus 2 is equal to 0. So we would add 2. So x is equal to 2 and y is equal to 0. At this time, this is so hard even for me to remember sometimes. I'm not gonna lie about that. You have to go back and go, do I have any holes? We do, because we had something that canceled out. So it's possible that one of these will say we have one and we don't. We have a hole at x equals 2. So we actually don't have an x-intercept. If you look at your graph, it looks like, I mean, if you look at x equals 2, it would be right here. And I don't know if I can make this bigger, but at x equals 2, it's actually a little bit above that, but there's actually a hole. It doesn't go through the x-axis there. I mean, you can see that. It looks like on the y-intercept, though, we should have a y. it should go through the y-axis maybe at 1. So let's go back and look at that real quick. So the y-intercept happens, this is a hole, doesn't, not there. The y-intercept happens when x is equal to 0, find what y is. And so if you go back to your original and you plug in zeros for x's, all the things that have x's are going to cancel out. I'm left with -2 over -2, which is 1. And that's what we thought. We can see that from our graph that we had a y-intercept here. Okay. In order to finish this graph, we need some additional coordinates. So we could get those from our table. I just went ahead and wrote down, I moved it back to like -3, and I just jotted down everything from -3 to +3. I looked at my table on my calculator and it said -3 is -1/2, -2 is -1, -1 gave me an error because at -1 there is an asymptote. 0 gave me 1, 1 gave me 1/2. 2 gave me an error because there's a hole there. You're exactly right. And that's what you're going to see on your table when you have holes or asymptotes, vertical asymptotes, that is. You're going to see errors there. So let's see if this is enough for me to plot this. So I have a point at -3, -1/2, -2, -1. -1 was a 0, or I'm sorry, -1 was my asymptote, I guess. But problem there. 0, 1, that was my y-intercept. I already plotted that. 1, 1/2, and 2 is a hole. I'm going to put it on the graph just so we can recognize that it's there. And then 3, 1/4. So it just gets closer and closer. So it kind of does something like this. It does not go back up like I just made it look like, sorry. It goes down, it gets closer and closer, but it doesn't touch it. Okay. So that is 8.5. 8.6 on Monday. The review is on Wednesday. So that's kind of where you want to be, is you need to be trying to finish 8.5 to be where we're at right now. I know it's not due till the next Sunday, but it's a good idea. If you go ahead and stay where we're at, you're going to be more successful because you're going to be understanding what we're